Okay, so what's the usual definition of, well, say that we have this function that we have here an input, this t, and it's outputting whatever, right? Let's say that here it's any vector. Doesn't really matter. So the problem is if we go directly to the definition of derivative, we are going to be in trouble, right? Even for this function. Because I'm just here creating what is the definition of this. And I'm going to ask who has like some problem with this definition here, right? And which ones? There are a couple of problems. So remember, t is this, same as delta t. But this is applying the definition of just derivative, right? So does anyone find a problem here? So t does not belong to the same. Yes. So this thing, it will not be part of the group. Right? Do you remember? You can do a summation of matrices, but that doesn't mean that the result is going to be on inside the group. It's going to be an element. Well, we don't know what that is. But if you want to get an element of the group, the group operation is matrix multiplication, right? So in this sense, this slightly doesn't look so good. What else? We have here subtraction of two functions. This is kind of okay. No? Yeah, okay, maybe. And then we have here this thing dividing, right? So this thing, what is this thing? It's a matrix, right? So this also creates like some problems. So these little increments on the matrix, we have said that they have some structure, but we cannot really apply them directly, right? So what is this thing, right? Are we dividing by a matrix? Is this the inverse? And actually this should go to 0. What is 0 of this matrix element? So the definition doesn't really apply here, right? We need to change slightly things. And this is the problem of today, right? We are going to find a way to describe gradients, which you will see by the end of the class, hopefully, that this form is very, very simplified. It's not that there's a closed form and then you just apply. No, it's that the result is very compact, you will see. And with that, what can we do? Well, so we can do many things with gradients, right? We can do many things with Jacobians. Which things? So we have discussed. It's useful for filtering. It's useful for covariance propagation, right? We have used basically first order approximation everywhere. Yes? We have it? We have used it? Yeah. So most of the times, yes. What is our solution to nonlinear functions? Linearize. Remember what we had here, right? So we had an observation function. What do? We linearize, right? So we are going to see that there's an equivalent actually for this operation as well. Okay, so let's find out what can we do with this, right? Definition doesn't apply, so we need to change like some things in our definition, right? And here we have two methods, right? To obtain derivatives. The first one, let's say that it's a little more general. And it's basically a first order approximation. Okay, so we have the same function, right? Remember, this function f is mapping from It's mapping from a transformation, a rigid body transformation, into whatever other space. This thing, by the way, could also be we will explain later what is this, right? If the image of this function is another rigid body transformation, right? So that's a little to think about. For now, we have a vector, right? This method, by the way, could also be used as this kind of any output. And the approximation that we are going to do is the following, right? So we have this function. Let me write it again. And here, yes, well, that doesn't matter. So what we are going to define is a new function, right, on the following way, right? So we are going to have this function instead of now depending on a rigid body transformation. This is going to depend on a vector that are the coordinates of the Lie algebra group, right? And I'm going to write later exactly what this means, right? So basically this goes to x6, and then this is going to be to any whatever image we have, right? So how can we do this, right? So what we're interested is actually in calculating these increments in transformations, right? And everyone agrees that we have a way to define new transformations as a sequence of other transformations, right? So it's not that you always need to propose a new variable. We could be using whatever we had before, like in this case. This is going to be over t. And then in our new variable, instead of being just this, right? Imagine this. It's going to be this, right? And this is the little increment that I'm talking about, right? So this is going to be the exponent of these variables, right? And this is going to be our new variable. When you change over this, we are going to be defining not a perturbation with respect to the transformation t, but with respect to a little change to the transformation of t, right? So it's this way. If you were thinking in terms of usual differentiation, here what we have is the final update, right? So you do what we were doing here is x plus delta x, right? We cannot really do this now, right? What we are going to be doing is this little increment. Okay, so yeah. So let me write it this way. Right? This new input, what I'm just adding, so when you evaluate this at increment of 0, what is this? This is the identity. Right? So we are not really doing anything. When this is evaluated at 0, this increment is so small that we are not really changing. But what we're interested in is do a derivative with respect to these increments. Right? So the notion of perturbation is not really differential here, but it's just a small change. Right, and then we'll see how the output changes with respect to each of these increments. Right, that's the idea. So that's the idea also for differentiation. Okay, so this new function, I'm just going to call it f of subindex t, and then this is just going to depend on these manifold coordinates. Okay. Everybody agrees here. I'm not doing any assumption, anything. I'm just changing a little this is a change of variables, assuming that here this t, we keep it constant, whatever it is, and then we just care about these little increments in the transformation, right? Not the full derivative with respect to the transformation. That will be a little, well, that can be done, but this method, I think it's much more clear, right? So what we're interested in is you perturb this. Oh, no. Yeah. You perturb this, and then what is the increment on the output, right, of your function? How this is this, and this is basically the definition of the differentiation, right? Let's put it back here. So you see this thing, right? We want to see exactly how this thing changes, and then we'll see what can we do, right? If we can just push these increments to the infinite, which is what the definition does, but basically what we are defining here is these increments on the function, and here, instead of doing a differential of this matrix, it's going to be a differential just on the manifold coordinates. Okay? Okay, so we have this new function. Now, what comes next? Yeah. So for this, I'm going to give an example, right? Because this is going to be different for each solution, right? And the example in this case is transforming a vector. For now, the only thing that we have done is redefine a function. No assumption, nothing new, right? But you will see where the approximation comes from and why this is called a first-order approximation. So we transform a vector. That means that we have this function, right? Our f of t equals this. Right? We have a point in homogeneous coordinates. We multiply by a transformation. And then this is the result of our function. Right? Okay, okay. So let me redefine this function then as we have just discussed, right? Instead of just being a function of our transformation, let's say that here we have some input, whatever it is, it doesn't matter. And then we want to calculate how this changes in the input, in this case just around these delta chi increments, actually affect the output, right? So this new function, it's going to be as follows. Okay, so far nothing, but it's a little detail, so everything should be very clear. Please answer a question there. This thing? It's the same, it's the same. Yes, so in the next one, what I'm doing is directly substituting, like, so this is what the function is, right? But if you want, you could be writing f of exponent of multiply by t, and if you do that, you're going to get this, right? Right, so the only thing that I'm substituting here is the input. Now the input, remember, we cannot really derive now with respect to the full matrix in the classical way. We are going to find these little increments in your whatever input it is, and for that we need to add this term, right? But we know that composition of transformation, this is still a transformation, right? And the idea, you always need to have this very clear. So what we are doing here is perturbing the input to see how much the output is perturbed, right? As any definition of differentiation. Okay, so this is our classical vector transformation with this little extra term here, right? Now, I'm just gonna differentiate. And for this, you will see that actually we can use like almost, standard rules for differentiation. Okay, so what I've done is I have just substituted this function, and the derivative now it's going to be with respect to this increment of the transformation, right? So if we do this, what can you tell me about these terms? Do they depend on delta chi? No, right? No, they don't depend. So we are just going to take them out. They are just constants multiplying this gradient, right? So let me put it this way. So this equals then, I'm going to go very slowly here. Remember that the order here matters. So you need to be very careful. You cannot really take a constant and put it like on front, because then this will not be equal. Right? We are just taking this constant vector. This is a vector. Well, transformation multiplied by a vector, it's a vector. And then here we are just maintaining those parts that belong to, that are a function, right, of the variable that we are deriving. So far everyone agrees. Yes, good. And this is where we are going to do our first order approximation. So if you remember, the exponent was like a long list of summations, right? So remember, the exponent actually comes from the Taylor series. And what I'm saying here is that, look, forget about higher order terms. You don't care about them. You just care about first order term. Why is that? Because actually this increment is going to be small, right? On the limit, this is going to be 0. So you don't care about things that are squared or cubic, right? They are just going to be very small. So this is an assumption or an approximation we are doing here, right? We are just approximating by this. The exponent function becomes just a linear function, right? You cannot really do that if you were like in other kind of, if these variables had like a higher value, whatever t has, right? So if you do the same thing, the exponent of, well, coordinates of t, then this approximation will not be so clear, right? So that's the advantage of doing these little increments with respect to the identity, right? Everyone sees this advantage, right? So we are close to 0, and this approximation is kind of good. And then we have this. Okay, so now let's see what happens. Let me write here what is the structure of this. I don't remember this thing always. Okay, so this was the definition that we gave, first of all, remember from this block of matrices, this is the skew-symmetric matrix, and remember that then later the Lie algebra looks like this, right? So it's a block of skew-symmetric matrices and some elements here. And then here we have a bunch of zeros, obviously, right? Because if you remember, T actually looks like this, right? So if you have a differential form or a tangent space of this transformation here, this last row doesn't change, so it should be 0, right? Okay, so we have this, and if you substitute this here, then we are just going to apply like differentiation rules, right? In this case, it's going to be for each component of this 6-dimensional variable, right? Remember that is delta psi 1. Right? So this is our vector. What we are going to do here now is just do the differentiation with respect to each of these variables. Remember, by the way, that this is theta 1, or if you want delta theta 1, theta 2, and finally this is rho 3, right? So what we were doing is just stacking, first of all, the variables that depend on the orientation or rotations, if you want, and the second part is the one corresponding to translations, right, or linear velocities. So we have this, we have this structure here, we have this matrix. What we are going to be doing now is, for instance, we just derive with respect to, let's say, variable 1, right? And what is variable 1? Yes. This is a 6 by 1. Yes, correct. And this is a 4 by 4. hold on. You are almost right, but you are skipping one step. So it's true, it's true. As a result, we are going to have a tensor, right? So things are not getting easier, but you will see in a moment that yes, actually they do. We have another question. Which matrix? This matrix? This is the structure of the Lie algebra group, right? So here what we have is a skew-symmetric matrix in this block. We defined Y last time, remember smoothness, and then this term is related to linear velocities. So the structure of this, it's not exactly from the twist, right? Remember that what we were doing here is evaluating the twist at T1, right? So there was this physical meaning and then the mathematical definition that we use, right? So in this case, these were actually angles. This is after applying like constant angular velocities and linear velocities, but at the end you get the same structure, right? So this is your Lie algebra group. Tangent space, you can also call it, right? Or twist if you had like angular velocities and linear velocities. But the structure is this, it's 4 by 4, right? Okay, so for one of these derivatives, right? I'm not going to go now for the tensor case, but for one of these derivatives, we come here, and then what we have is that if you do the derivative of this, you're going to have a bunch of zeros. I'm just following this, right? And the red one, these red values are just the one that belong to, right? So you're going to have matrices that look like this. And what are these matrices? Actually, this is the matrix, the matrix of generators that we discussed before. So if you have like this matrix, this group, and you want to generate the manifold, what we did is we had this summation of generator matrices multiplied by some component. And if you do 6 of them, 6 of these generators, then at the end you will get this structure. But interestingly, you have the same result when you calculate this for the derivatives, right? So at the end, doing this first order approximation, let's put it here, this goes away. And then here, each of these components are just going to be derived, right? Each of them. And then we are going to have this very simple matrix, right? Just some zeros, some ones, and things like that. Okay, so getting back to our example, we were deriving this function of t, right? So that means that here we are going to have the first generative, and then we are going to have this. Okay? In general, you see that for each of these coordinates, we are going to have like different of them, right? So in general, you could be writing this way. Right? If you want, this is kind of the vector of generatives. So this is 6 by 4 by 4. Indeed, this was a tensor. But you'll see that things get simplified now. And how is that? So here what we have is, let me write it this way. Okay, we have a 4 by 4 matrix, right? We have another 4 by 4 matrix, and here we have a vector, right? So if you do the result of this is going to be a vector, right? Actually, you can do it later at home if you want, but if you, for the first generative matrix, the result that we are going to get is, well, basically you can go here, but I think it's, well, I'm not going to do it. The interesting case is this one. Here you have this thing. Okay? here you have a vector, right? A matrix multiplied by a vector. So if you group, so whatever is the result of this, see that this thing is very sparse, right? Not many elements are going to be multiplied by this. Okay, if you want, let's do it. I mean, I don't have this prepared, so you will help me. Okay, so we have this multiplied by P1. So here we are going to have a 0. Here we have B3. And here we have B2. Right? Now, the interesting thing is if you do this for G2, we are going to have something like this. Oh, fuck. So this is V3, and this is 0, and this is minus P1. And the same happens for the other generative. The interesting thing is that this tensor, which at the end gets multiplied by a vector, right? So there's going to be contraction. The dimensions of this are going to change. If you rearrange many things, you are going to have something like this, right? It's going to be this vector. Remember this operation, what it is, right? This operation is the skew-symmetric matrix. And here, okay, what I'm doing is just the three-dimensional vector. So I'm forgetting about the homogeneous coordinates, if you want. And then on the second block of this matrix, it's going to be just the identity. Why? Because the generator of these variables here, it's going to be all zeros except 1, right? So then you'll see that things disappear very quickly. And then here, it's just going to be an identity. It doesn't matter. I mean, for the it doesn't matter what's the value of this vector, right? Here, the derivative is going to be like this. And let's think about the dimensions, right? So I have discussed that this is a 3 by 3 non-homogeneous. So this is a little abuse of notation here from my part, right? Because remember that P, in this case, must be homogeneous, and here we do the multiplication, and then what I'm doing is whatever is the result, I forget about fourth coordinate, and then I just do the this is skew-symmetric matrix, and this is the identity, 3 by 3, right? So this is a 3 by 6 matrix, right? So you were saying before, but the derivative of the exponent, actually, it's a 6 by 4 by 4 matrix. That's true, but we are contracting it multiplying by a vector, right? And this is the first compact result that you will get, right? So if you were just transforming a vector, this is the result that you will get, right? You just need to do a cross, well, kind of the skew-symmetric matrix of whatever it is the transformation you have. For this, actually, you will see that you need starting conditions. But we have also discussed on this. You need like starting point. It's not going to be the same for different starting points, right? So the derivative actually depends on what is your, this, let's say, given point. And then this is just the identity. Okay. So, can you repeat it? This hat is when we build a skew-symmetric matrix. So in this case, this is this, right? So the hat of building, this is a three-dimensional vector. When I write hat, actually what we are doing is the construction of the skew-symmetric matrix, right? Yeah. Okay. So it gets compact. You don't really need to memorize this, but you need to understand the procedure, right? So what we are doing is just, let's say, simplifying a little things just by considering exponent to be a linear. And that's true when these increments are very small, right? On the limit, you put them to 0. So, yes. So the term G bar is a step of G bar. Yes. No. So what I do here is I multiply this tensor, right? There's a 4x4 matrix for each of the components, right? In this case, 6 components. Each of them are like this, right? And then you multiply this 4x4 by this 4x4 by this vector, and as a result, what you get is a vector. And we should be getting 6 vectors. So if you put them this way, you just move them, and then you create some sort of a matrix. So this is this should be, if we forget about this coordinate, this is a 3x1, right? By 6. So what I'm doing is putting each of these columns here. Yes, because at the end, well, you can think about it just as a construction, right? As a contraction of this kind of a structure. So you could be using just this, and then you need to operate these matrices as well, right? So this actually looks also like a matrix. So it's not that I'm rearranging things. So if you see, we have lost 1 dimension, but here this is still a 2-dimensional array, right? So here we just have 3 components, and here we have 6. So the result is this. You can try this at home, by the way. So you take the generator, you differentiate. Here, by the way, the note is that I'm applying standard differentiation tools, because here what we have is a matrix differentiated with respect to 1 variable, right? So this goes to 0. I mean, when you do this, the limit goes to 0, right, on these increments. So there's not really a big magic happening. There's not a big assumption. The first order, I think it's an accurate way for calculating gradients. It might not be true for Hessians, but, well, you don't care for now. So, yeah, that's it. So what we have done, broadly speaking, is we have adapted slightly our function to be differentiable. And that's not really by changing things. It's just by taking the definition, changing the input, right? And then assuming that the input is going to be a composition of 2 transformations, right? And one of them is going to be infinitesimal, and the other is going to be whatever you had, right? Is this idea clear? Because this is kind of the important takeout from today. Yes? Yes. Okay, you will see it later, like in action, this thing. Okay, what else? There's a second method, which is small perturbations. Small perturbations. So you have this well explained on the document, right? I'm going to just give you like the hints of this function, of this alternative way of calculating things. The other, let's say that it's a very general method. Sometimes, especially when you have a vector, things get simplified, but maybe others, they will not get simplified, right? So you will need to carry on this tensor, and well, you will be calculating things, but that's still fine. The second method, it's based on the following function, right? So we are going to have a function that has like some input, a rigid body transformation. This is not new. What is new is now the output is going to be directly in SE3 as well, right? And I just want to discuss like an idea, which I think it's going to be, you can further then develop this by taking a look at the notes, but the idea should be clear, right? It's the following. If before what we did is transform slightly the input just to be on nice coordinates that we can transform, such as the manifold that Lie algebra provides us, here we are going to be doing the same thing, but you need to do this at the same time, right? Not just from the input, but also from the output. Why? Because if you remember on the definition of derivative, we have this, right? So if the image of this function is still a rigid body transformation, what is this operation, right? That's not valid anymore. From definition, okay. Okay, so what's the idea? The idea is that this function it's going to be perturbed, right? This is the same thing as we did before. We are perturbing the input slightly. And what is this equal to? So we know that the output of this is going to be a group of the element. It's going to be an element of the group of rigid body transformations, right? So we cannot really just say, yeah, whatever it is, and then we are going to apply here like a summation or subtraction. What we need to express is that these little changes inside the group, right? And for that, we are going to say that this should be equal to small perturbation of this function, right? So you see the idea. This is the input that we are slightly perturbing. And now in this case, what we are saying is you cannot really perturb the output the same way, right? You need to perturb it in a way that belongs to the group. Why? Because this thing belongs to the group. But still, the output, okay, whatever, this thing, let me use this thing. Yeah. And then whatever is the output, we are going to perturb it like this way, right? So it's going to be a perturbation. If not, we cannot ensure that the output of the function is still in the group, right? So we are always stressing on the same thing. It must be inside the group. All this is because this thing has to be inside the group, right? So it's clear, this idea on how to calculate then derivatives, because the derivative then it's going to follow from this. So if before what we did is just slightly change the input, and now we were deriving with respect to a 6-dimensional vector, now what we are going to be doing is slightly similar thing. The input is also going to be a 6-dimensional vector, but the output it's going to be a 6-dimensional vector. And for that, we have tools, right? For that, it's just common differentiation tools. Right? But for transformations, that's not clear. We cannot really do summations, because then we are going to get a result that is out of the group. It doesn't matter if it's small. It's going to be out of the group. So you cannot sum. You cannot subtract. You can always multiply. That's the only operation. Okay. It's kind of clear, this. And then what we can do is the following. So I'm just going to operate this expression, right? And then this epsilon, it's going to be this. It's going to be the logarithm of this g function. And then here what we need is this, right? So I'm just slightly changing things. And now what we have is, as I said, an output that this thing is a 6-dimensional vector, right? And now this output depends on an input that is also a 6-dimensional vector. So if we before, what we were proposing is this, the derivative of g with respect to any transformation. After doing this slight modification, this derivative is going to be equal to this, right? So the derivative of epsilon with respect to these inputs, right? So this is input in the manifold, and this is output in manifold. Okay, I leave this for you. You can follow the document. It's well explained, so it's like it's not really like, doesn't go very technical. It's showing like some examples actually on what to do, and then you will see that this gives also like very compact results. Okay, let me also discuss a little detail on this, right? So now the logarithm appears in our derivatives, right? But in fact, I have also discussed that the logarithm is a very good way of expressing errors. So take a look at this, right? Let me write it this way, right? So, okay. Let me write it this way. We have one function that we have kind of perturbed, and here what we have is this function to the -1, right? What's the result of this if delta is 0? The identity, exactly, exactly. So this is outputting whatever result as a rigid body transformation. This is another rigid body transformation, but here the input, we are saying, look, yes, we are not really perturbing T. It's just going to be whatever it is, right? So if this is true, then here we'll have the identity. And this is an interesting part. So what is the logarithm of the identity as we have defined before? The identity, remember, is the, well, the identity is the identity element also in our group, right? So in the manifold, this equals 0, right? It's going to be a vector of 0 coordinates, right? And why is this useful? Because now what we are saying is, okay, so this is going to slightly change. This G is going to be slightly changed by whatever perturbation you want to add, right? And then what this logarithm is actually measuring is this difference, small differences, but still like some differences with respect to this, right? So you are going to have here G, and you are going to have here G. Okay, so if you want, this is J prime, and this is J minus 1, right? And this thing, it's not going to be 0, right? So in this case, when you apply, why it's not going to be 0? Because when you perturb it by delta, this is going to change slightly. And what we are looking for is how much we are perturbing this output with respect to the input. Okay, so another definition is logarithm as a measure of error, right? So in this case, we forget about G, right? We have T. And then imagine that we are really observing like this T. This is another different function, right? And we have this form, right? So what we are saying here is that if the observation is exactly our T, this thing, if these things should be matching, this is giving you like a measure on how far this thing is, right? If you want to go a little farther, we can do it this way, right? So this will be the norm of a 6-dimensional vector, right? And actually this is a measure, this is a distance, right? On with respect to elements, right? So okay, let's change it maybe. What is this? Yes. LN? You mean here? As distances. Okay, so this function, by the way, is symmetric. So it's the same as why? Because, well, this was another property. Did anyone take a look at the properties in the document? So there was a very interesting one that is the following. The inverse of this transformation, it's just this. Okay, so then you can do some derivations, and then you will see that these distances are useful. Okay, so what is the result for this? That then you can have like even more. You can have a chain of transformations, and then we are always going to be looking for how close, how well aligned all these things are. And at the end, this is the result. We are going to be looking for things that, for instance, this, and then this. Right? So we are going to try always to close kind of circles, right? We always want to do this, if you want this distance small, right? This distance is small. And that means that you basically follow like long paths of this could be, let's give an example. This is our transformation of I. Transformation of I plus 1. And this is the transformation of odometry. Is this thing familiar? So the transformation function that we were using before, actually it's just a sequence of rigid body transformations. So in this case, what we were saying is that T1 multiplied by T odom should be equal to, or if you want to put it, I mean, you can play around with any order you want, right? As long as this thing is the same. No. Yes? So I'm just multiplying here on the right, the inverse. Okay. So if you want to go a little deeper into this topic, here on the notes, you will have more material, right? So this is explained a little better. But the second, I think, important idea from today is that actually the logarithm is just measuring distances. It's not just that we measure like perturbations in the for the derivatives, right? This was the initial condition, right? So we wanted to perturb things with respect to coordinates in the manifold, which is a vector. But as a result, we also found that when we do this kind of operation, what we have is a nice and well-defined distance, right? So remember, the manifold resembles Euclidean space. In this sense, we are preserving distances between transformations. And this is very important, because later, when you apply like things to state estimation, you are going to be calculating like, what is the residual, right? So ideally, everything matches. Residual is 0. But if not, you want to perturb just to make it smaller, right? Okay, anyway, today's topic, I think, requires for you a little more practice, a little more thinking, digesting all this. Let's just keep, and I think what we are going to do in the seminar is just work on this idea, right? So we are going to have a function that is transforming a vector, and then you are going to be using there the, these derivatives, right? So we are going to do a short break. Yes, please, one question. We need to, sorry, I didn't get that part. It's one, so the question is, we just need this to linearize function. This is one application. But actually, calculating a derivatives has like other applications, right? It's not just that. We've seen that optimization can also be used here. On problem set 4, you will see a different kind of usage of this, right? Which is you will be obtaining second-order derivatives as well. So with this, you can still do many things, not just linearize, right? Linearize, let's say this is the first step, and this is. But once you calculate gradients, you can do many, many, many things. Right? It's a very, very useful thing. I think this is the only reason why we have spent 2 days explaining transformations. It's because derivatives, when you are working with 3D poses, become much easier. If you want to work with other representations like quaternions or Euler angles, double quaternions you were using, then derivatives are not that clear, right? You need to work a little more in the math, much more. I think this is a little more natural approach, right? So in this case, just think about this as a cool tool that you can use. And actually, you are going to use after the break. Okay, so let's do a break, and we'll get back in a moment.